Okay, so before we move on to the next component of Earth system science, which is really plate tectonics and Earth's interior, we took a brief detour through long and short-term climate records, and we talked a little bit about how they're formed. We'll discuss that more as we get into the carbon cycle in more detail, but we established how the climate works at this point more or less, and so we're going to start talking about that at this point and then follow up in future classes. But what's shown here at the left is known as the Keeling curve. It's showing CO2 levels in the atmosphere as they have risen over the past half century or 60 years. That's this kind of average increasing trend. But if we look at 1 year, what we see is that there's this annual cycle where CO2 rises from October or so through April and then decreases in the atmosphere from April until October. And that happens every year. And you might equate those brackets of time as winter time and summertime. That's certainly true for us here in the northern hemisphere, but it's not the case in the southern hemisphere. It's the opposite, right? But it is in fact the reality that the northern hemisphere has an enormous amount more land mass than the southern hemisphere. There's lots more continents. And so there's more forest and there's more vegetation in general that grows during the summer in the northern hemisphere than grows during the summer in the southern hemisphere, right? And so because of that unequal distribution of land mass, kind of shown here, we have more photosynthesis turning CO2 and water into organic matter and oxygen during the months of June, July, August than we do during the months of December, February, and January, right, when it's summertime down here in the southern hemisphere. Right, during winter time in the northern hemisphere, deciduous trees and other vegetation dies, drops its leaves, and the like, and the carbon cycle is dominated by respiration, which takes organic matter and oxygen and turns it into CO2 and water. Excuse me. Okay, and so throughout the course of a year, CO2 levels increase during the winter time in the northern hemisphere and then decrease during the summertime in the northern hemisphere as a result of the relative balance of photosynthesis and respiration and the unequal distribution of land mass. All right, but of course we have seasons at all because the Earth's axis has a tilt. Excuse me. Okay, the Earth's axis has a tilt, and so because of that, the point at which the sun's radiation intersects the Earth's surface at a 90-degree angle, the highest solar flux, we would say, is in the northern hemisphere during June, right? And it's in the southern hemisphere during December. That would be this is the summer solstice for the northern hemisphere, June 21st. That's when the sun's rays intersect the Earth at a 90-degree angle at the highest northern latitude, which is known as the Tropic of Cancer. It's 23.5 degrees north. That reflects the fact that the Earth's axis has a 23.5 degree tilt. Okay, and so again, right, we're receiving a higher flux here than up here that generates, the energy distribution that we see and drives atmospheric circulation, et cetera, et cetera. But it also means that in the northern hemisphere, we get more radiation, right? And so more forests grow. Okay, so that's pretty straightforward. That's a yearly variation, and we've seen that generally speaking, CO2 levels are increasing. But if we go back in time, we see a very different picture. This is a long-term record that comes from ice cores. And it shows, we're currently up here at about, we're well over 400 ppm now, up toward 420 ppm. But if we go back about 200 years, back to 1,000 years, it's pretty consistent, right? And we've been monitoring CO2 for the last 60 years or so. But moving back in time, we have to use different records. In this case, these are ice core records to reconstruct CO2 levels in the atmosphere. The red line is the temperature going back, and it's significantly warmer today than it was 200 years ago, the Earth on average. And moving backward in time, you can see there's this kind of gradual decreasing trend, in fact, that we were in for the last 1,000 years. Excuse me. Okay, so we get these records largely from ice cores, like I mentioned, and we reconstruct them based on gas bubbles, like we talked about in class, and also water isotopes, both hydrogen and oxygen isotopes. That's largely how we reconstruct these records. And so oftentimes you'll see carbon dioxide and temperature, and the temperature is based on some proxy. We don't have a thermometer trapped in the ice necessarily. We have different techniques that act as kind of proxies for thermometers. And oxygen isotopes are one that are commonly used. They're very robust and fairly easy to understand. And so we talked about how those work, and we'll touch on that briefly in a few moments. But you know, we drill these ice cores in places like Antarctica, Greenland, mountain glaciers, and we can reconstruct records. There's actually ice preserved for almost 1 million years. This particular ice core from Vostok, Antarctica, goes back about 400,000 years. There are other records. I think the next slide shows 800,000 years. And so we can see over this very long time period that the temperature has fluctuated like this, and CO2 has fluctuated in a really similar fashion. They're almost perfect mirror images, or not mirror images, they're transpositions of one another, right? And you can stack them up and see that. Okay, and so the question now is why is that? We took a brief detour through oxygen isotopes, and so I'll end this video here and then and talk briefly about oxygen isotopes, and then return to this climate record and talk a little bit about how it forms and the feedback relationships that exist in the Earth's climate system.